listeners, you're welcome to today's episode in our series, in our channel, African Science and Humanities Review. In the past episode, we have been considering the laws of nature. We started with the laws of science, and we have been considering various branches of science. We considered the physical science. We also say you can talk about mathematical sciences, you can talk about biological sciences, you can talk about chemical sciences, then we can also relate to applied sciences, engineering. So we considered the laws of physical sciences, then we moved to the laws of mathematical sciences. We started the laws of mathematical sciences in the last episode. Today, we are continuing with the laws of mathematical sciences. In the last episode, we considered some laws of nature relating to identity, inverse, commutativity, addition of an element, transitivity, distributive law, and so on and so forth. So today, we want to examine the laws relating to sets. What is a set? A set is a collection of elements. And then we are going to relate that to some of the basic laws of statistics, and then we are going to consider some simple application areas of the laws of mathematical sciences. Please sit back and enjoy today's episode. You are welcome. Some basic laws of sets. So we can see this first diagram. This type of diagram is called the Venn diagram. We can see universal set, that is the set of all possible subsets of a universe. And of course, the word universe is equivalent to the normal universe, to nature, with respect to the phenomena we are describing. Here, we have two sets. Set A, we have three sets actually. Set A, set B, and then set C. So we can see that set A is occupying this portion, set B is occupying this portion, and set C is occupying this tiny portion. And if you look at it properly, this portion where set C is occupying is the intersection of set A and set B. By intersection, we mean it's a portion where we can find elements of A. If you look here, elements of A, because A extends here, and we can also find elements of B. So in mathematical terms, we are saying that the intersection of set A and set B is not empty. As we can see, it's not empty. When we consider the second diagram, we'll see that the intersection is empty. Here is not empty. So when it's not empty, we can talk about the law relating to the number of elements in this universe. So the number of elements, well, we can say A union B for simplicity's sake. So the number of elements in A union B is equals to, by formula, by law, the number of elements in A plus the number of elements in B minus the number of elements in C. This can actually be proved. It's a law of mathematical sciences, and it's a very good proof. Students at the higher level and first level mathematics students in the universities and higher institutions, they juggle with this type of problem. So we can look at the second example here. Of course, as I said, this is called a Venn diagram due to the mathematician who was able to formulate this kind of diagram for analyzing, for solving this kind of problem. So in this case, we can see that A is not touching B. So A and B, they don't have any elements, any element in common. So when that is the case, mathematically you say that A intersection B is empty, where this symbol is called the empty set. That is, there is no element in the set, unlike this diagram. So when this is the case, in which A and B, they don't have similar elements, the number of elements in A union B is equal to the number of elements in A plus number of elements in B. Because in this case, this third element, NC, will be 0. So if you look at the first diagram, the formula would have been NA union B is NA plus NB minus 0 here. So that's why it just reduces to these first two terms when A and B don't have elements in common. So this is a very important law of mathematics, the law of sets, and it has a lot of applications in real life, in diverse areas as social sciences, accounting, finances, many other areas apart from the natural sciences and engineering. So now let's move to consider some basic laws of statistics. In this consideration, the symbol P is representing probability, and A and B, they are events, and S is an event space. By talking of event space, more like we are talking about the union A, all possibilities with respect to the space we are talking about. And when we talk about space, it's the normal space, the air space, the space around where this thing is moving around is a space. All these physical phenomena have been translated into some mathematical terms. So we have some abstract mathematical relationship to describe virtually everything in the universe. So these are some of the relationships, some of the laws. Of course, we can't consider all the laws. So let's look at some of the basic laws of statistics. So serial number 1, probability of A is equal to the number of points in A all over number of points in S. For instance, if you look at this diagram, if you want to find the probability of this A, let's use the one that we don't have intersection. So the probability that A will occur is to count the number of points in A, the elements in A, and then you divide by all possible points that you can have, all possible points you can have here. So NA all over NS. That's the first law of statistics. And when you say it's a law, you can always prove it and to always obey the rules. The second one, we are saying that 0 is less than or equal to probability of A less than or equal to probability of 1. What we are saying is that the probability of A, the maximum value that the probability of A can attain is 1. And the minimum value that it can attain is 0. That is to say, this simple inequality is saying that PA, because it says 0 less than or equals to PA, if you want to put PA in front, then PA is greater than or equals to 0, but it is less than or equals to 1. So the probability, when you are talking of probability, it cannot be a negative value. It can be 0, but it can be negative 0, and it must lie between 0 and 1. We move to the third law of statistics. One of the laws of statistics we just described as the third law. Technically, it's not necessarily referred to as the third law. So if your A intersection B is empty, just like you have here, the probability of A union B, when we say if it is empty, the probability of A union B will be probability of A plus probability of B minus, if it's not empty, this is where we are considering, because if it's not empty, you can see you have components for A, B, and C. So if it's not empty, so this is the one we are describing. So if you just change this to P, A union B is equal to PA plus plus PB minus PC, because C is A intersection B. So that's what we have there. And if A intersection B is empty, just like this second diagram, instead of N you put P, P A union B equals to PA plus PB. So we can see that it's still a consequence of some of the basic laws of set. That's what the statisticians, the mathematical statisticians, they apply here. Because there is consistency in nature, there is consistency in mathematics. So that's where you have this. So let's look at another law. That's law 4. Law 5. This is called conditional probability. You can see that the same probability of A giving B, giving an event B, is equal to probability of A intersection B all over probability of B. We remember that when we talk about probability of A, the simple illustration is to consider a die. A die has two faces. It could be tail, it could be head. So the S, the number of points in S will be 2. Tail, you count as 1. Head, you count as 1. So the probability that is going to be a head, you can only have one of them being head. So it's going to be 1 all over 2. And of course, you can see 1 over 2 satisfies this. 1 over 2 is 0.5. It lies between 0 and 1. And probability of head is also the same thing as the probability of tail. You can only have 1, and then the space can only have 2 points. The same thing can be applied when you consider you are playing the game of Ludo, okay? And you are throwing a die. The first case we are considering a coin. When you have a coin that has two sides, the head and the tail. But when you are talking of a die that has up to, it could be 1, let's say 1, 2, 3, 4, 5, 6. Okay? So the probability is going to be 1, will be 1 all over 6. Okay? The probability that is going to be 2, 1 over 6, and so on and so forth. And there is also another law, which is when you add all the probability together, you cannot get more than 1. So this is called a conditional probability. That is, you have an event, A giving B. That is, B has happened. So what's the probability that A will happen giving B? The probability of A intersection B all over probability of B. This and this, they have this and this. They have application in a lot of applications. For instance, in the recent developments related to machine learning, artificial intelligence, you can talk a naive Bayesian system. So, but if A and B are independent, that is, they don't relate to one another, there is no relationship between A and B. That is, that when A happens, it doesn't have to depend on what B happens. Okay? And vice versa. Then you can say the probability of A intersection B, this one, will be probability of A times probability of B. And when they are dependent of one another, the probability of A intersection B, in this case, plus the probability of A, probability of B giving A. So it's more or less like substituting this. When A and B are independent, you substitute this here, and when A and B are dependent, you substitute this here. Of course, the concept of dependency, we are familiar with it. You could recall when you talk about the X and Y axis. Okay, you can say Y is equal to 2X. So whatever Y you are going to get will depend on the value of X. So Y depends on X. So that's a simple illustration of the concept of dependency and independence. And of course, just like you said, Bayesian theorem, which is very, very important in machine learning, artificial intelligence, the basis of that is this concept of conditional probability. And of course, I want to just mention a few applicable areas of the laws of mathematical sciences. We have mentioned machine learning and artificial intelligence. We can talk about logic system. The logic system is based on conditions. If this happens, this can happen, and so on and so forth. Then computer systems in general, but that's the basis of computer systems when you talk about the concept of logic, or, and, nor, and so on and so forth. I believe you have enjoyed today's episode where we considered the laws of sets, the laws of statistics, and some applications. In the next episode, we are going to continue with some of the other laws of nature. Don't forget that this channel is on the interrelationship among science, theology, and philosophy in nature. So we have been considering all the laws of science, that all the laws relating to nature, and then we try to segment the laws into laws of science, laws of theology, and laws of philosophy. We are still on science, and when we have exhausted the laws of science, then we're going to consider the laws of theology and the laws of philosophy. Thank you very much for staying tuned to this channel. Please stay tuned and expect consideration of other laws in the next episode. Thank you very much.